Now this signal that is being transmitted has to be identified by the receiver, right? It's an analog signal pretty much. An analog signal is one that takes on a large range of values from A and B, let's say. It could be minus infinity to infinity. It takes a range of values, not a particular discrete, not sets of values, not individual values as in case of a discrete signal, not zeros and ones like a digital signal, but a set of values. So at the receiver, what the receiver has to do is identify all these values. Right? There's a wide range of values that are possible in the message signal. So the possible values in the message signal is a large range. Now consider, we'll come back to that, right? Consider you're going for a picnic and there are a lot of people there. Okay, a lot of people. Okay, a lot of people there. Okay, a lot of people there. Now suppose someone asks you to identify which state a person is from, right? Just by looking at the person, what language he speaks, what what kind of which country he comes from, or anything like that. Okay, this is one possible set of questions that you could be asked. Another thing that you could be asked is to identify whether a person is a guy or a girl. Okay, so if you're asked to identify which state a person is from, that's not so easy just by judging the actions, because there are a number of states that he could be from. However, if you're asked to identify if it's a guy or a girl, there are just two possible sets. There are just two values in the sense that that guy could take. It could be either a guy or a girl, right? So it's much easier to identify if it's a guy or a girl. Again, if there were just two states, two countries in the world, let's say there was just USA and India, and you were asked to identify if it's an Indian or a American, that would be easy as ABC, right? You could say, oh, that's brown, that's an Indian, that's white, that's an American, whatever. So, alright, I'm not being racist here, I'm brown myself. So, if they're just two sets of values, let's say 0 and 1, then it's much easier to identify if it's a 0 or a 1. And when I say much easier to identify, I mean after the addition of noise through transmission. So if there's noise here, you can still say, oh, this is a 1, this is a 0. But if there's noise here, right, this value is completely deteriorated. So it's much difficult to identify what this value was. So that's the reason why we shift from analog communication to digital communication. So now in case of digital communication, we're just sending zeros and ones, right? But remember this, when it comes to the channel, through the channel we only send analog signals. However, they can be, they have to be then coded into zeros and ones. So you require coding and decoding apart from the transmitter and receiver and all that stuff. So there was this transmitter, there was this receiver, but you now also require coding and decoding, right? The channel. Now again, coding and decoding are considered to be a part of transmission and reception respectively, right? So it's not really identified as different blocks in your black box diagram. And why does this Windows keep coming up? And now I have to fix that. Now so to change a signal, let's say an analog signal, to something in zeros and ones, let's see what we can do. First, what we can do is, just take some fixed values at fixed intervals. Only take a set of values, enough that we can later approximate the complete signal based on those values. Now how do you know you can approximate that? Based on some theorems given by people like sampling theorem and all that stuff. So we're just taking discrete values. How do you change the color? Right, we're just taking some values so that we can later take these values. Right, whatever we're doing now, we have to do exactly the opposite at the receiver, right? Just keep that in mind. It's a communication system is like a mirror image about the channel. Whatever you do before the channel, you have to do the exact opposite after the channel, because the input and output of the system is essentially the same, right? It has to be the same if the system is ideal. The signal that has to be transmitted, the message signal, has to be the same as the signal that has to be received. So if you do certain operations on a signal and you want to get the same signal, you have to do the opposite, the reverse of those operations, right? So transmitter is like a mirror image to receiver. So it's a mirror image about the channel component. So later we could just use these values to form the signal again, to just join these values and form the signal again. The second thing that we do here is we take certain values on the y-axis, right? This is called quantization of the signal. And let's say 0, 0.5, 1, 1.5, and so on. And now we approximate the sampled values to the nearest quantization level. Okay, so this translates to this, this translates to this also translates to this translates to this translates to 0, this also translates to 0, this translates to 1, 1. So you're approximating the sampled values based on these quantization levels, and then you assign a binary code, which is a code consisting of zeros and 1 to each level. So 0 0 0 1 1 0 1 1, right? And now you transmit this binary code instead of the signal. So let's first translate this into the binary code. This is approximated to 0.5. Actually this is much closer to 1, but forget that. 0.5, so this is 0 1. These are closer to 1.5, so it's 1 1 1 1. This is closer to 0.5 again, 0 1. This is closer to 0 0 0 0 0. This is closer to 1, so this is 1 0. This is again closer to 1, so this is 1 0 again. So now we need to transmit 0 1 1 1 1 0 0 1 and so on. So how do you transmit this? I am sorry. Again. So it's gonna be 1 1, right? So how do you transmit this? You can just represent these by voltage levels. Okay, let's say plus V and 0 just by 0. So it's 0 1 1 1. I'm leaving some space between the two binary words consisting of two binary symbols each, and 1 0. There's some space here, some space here, some space here, right? Now this 0 1 is a binary word. This 1 1 is again a binary word, and each of these is a binary symbol. Alright, so if you have 2 bits, you can have 4 words, right? 0 0 2 1 1. If you have 3, you can have 8 words, so it goes like 2 to the power n. If you have n bits or n symbols, you can have 2 to the power n words, bits or symbols, right? We're gonna look at each of this in detail later, but now this is transmitted, and you get the this is just essentially called PCM. It's called pulse coded modulation, but this is an example just to show you how you convert the analog signal into something that isn't just zeros and ones. This you can later quantize this again. Let's say you have noise here. So quantization again would just cut off this noise by reducing it to levels. What is quantization? You just keep the steps, so every noise just goes out. This is the input output characteristics of a quantizer, right? And you can then reconstruct the sampled values to get the signal back, alright, using a reconstruction filter. Obviously you need coding this back to 0.1, 0.5, then you get this, these approximated values, then you reconstruct to get this. Of course it will not be the exact same signal, but an approximation of the signal. So that is why you don't see PCM going on everywhere around you, but this is one technique to do it. Now if you decrease the bandwidth, if these signals come closer, the symbols, two symbols from different words tend to overlap. This is known as inter-symbol interference, and the other things that we will talk about in digital communication.